So, recall what we did last time, where we sort of left off. So, we showed that if we start with a finite dimensional vector space, and a linearly independent subset of that vector space. So I'll call that set S, and I'll contain vectors v1 through vn. And I assume that this is a linearly independent set. Then S can be extended to a basis v1, vn, vn plus 1 up to vm of v. Now this looks at first like some sort of simple, obvious result, and the proof wasn't very hard in some sense, but nonetheless, this is a very, very important result insofar as it completely informs the way we think about manipulating vector spaces. And it's going to have a major impact on our ability to analyze the sort of group theoretic properties of vector spaces. So just to reinforce that idea, I'm going to look at some consequences of this particular result, some of which we saw last time in some form, others which are somewhat new. So let me just start by listing some consequences, and we'll just run through briefly why those things are true. So let's just start with the following. So let W be the subspace. So I'm just going to retain notation from the recall here. And I'm going to let W be the subspace of V spanned by the set V1 through Vn. Now recall we saw last time the word span means the set of things which are linear combinations of a particular set of vectors. So W is all things of the form C1 V1 plus ... Cn Vn is C1 through Cn range over the implicit field here, F. So running behind the scenes here is that V is over F, F being some field. And in general, it suffices to think of this field as being R, but that's not always true. Finite fields have weird properties, so you should bear that in mind, especially when you're adding finite sets of vectors. But for now, we're just concerned with these sorts of general results. Okay, so, and let W prime be the subspace spanned by the remaining vectors, Vn plus 1 through Vm. Well, then here are two consequences. Then, first of all, the intersection of these things is 0, but that's not really a major result. The point is more the thing that I'm about to write down, which sort of takes advantage of that fact, which is, and we have a linear isomorphism between the product of W and W prime. What's the product? Well, this was part of the reading for one of the sections in the last chapter, but just to refresh your memories, this is the set of ordered pairs, W, W prime, where W ranges over W, little w ranges over big W, and little w prime ranges over big W prime. There's a linear isomorphism between this product thing and V, where we just take a pair W, W prime, and we map it to its sum. So using a term introduced last time, can somebody give me a way of seeing fairly immediately that the intersection of W and W prime is just the 0 vector space? Yes? Yes, so that would be sort of, yeah, it has to do with spanning, but there's a much more critical thing. The thing that you really use immediately is linear independence. So it follows immediately from a sort of generalized notion of linear independence between these two things. Specifically, the fact that the cumulation of these two sets is linearly independent. Well, why? I mean, suppose I have something which is in W. Well, I can certainly write it by definition of span as A1, W1 up through AN, WN. And if I have W prime, I can write that as AN plus 1, WN plus 1, up to AM, WM. So these are just sort of general elements of W and W prime. And if these things are equal, so if I have these things being equal, well, then I can subtract them. So W minus W prime is 0. But that's this sort of non-trivial linear combination of A1, W1 up through AN, WN plus minus AN plus 1, WN plus 1 up through AM, WN. So just negate that. This thing equals 0. And since these should be V's over here. V1 through Vn, Vn plus 1, Vm, V1, Vn, Vn plus 1, Vm. Well, since these things are all linearly independent, by hypothesis, these things form a basis. All of these AIs are 0. So each AI must be 0. So the things that we started with must have been 0. So it's the linear independence which is telling us in like a completely essential way that the intersection of these sorts of linearly independent spans must be 0. Now let's move on to the fact that this thing is a linear isomorphism. Well, the fact that it's just a homomorphism follows pretty much immediately from the definition of vector space structure on the product. So how do you add things in here? Well, you add them component-wise. So if I have W1, W1 prime, and W2, W2 prime, you just add these things, W1, W2, W1 prime plus W2 prime. And if I multiply by a scalar, C times WW prime, that's just CW, CW prime. So it's pretty apparent that this map here must at the very least be a linear transformation. So is that pretty clear to everyone? Okay. The surge activity. In a word, where does the surge activity come from? Spans, exactly. The fact that V1 up through Vm spans. Because everything in V is by definition some linear combination of V1 through Vm. And so I take the first part of the linear combination from W and the second part of the linear combination from W prime. I add those up and I get whatever vector I wanted in V. So the surge activity follows from spanning. And then finally, injectivity, where does that come from? Yes? Linear independence, exactly. In fact, we've already shown the critical thing about linear independence, which is specifically that the intersection of W and W prime is 0. Because if I have, suppose I have W1 plus W1 prime equaling W2 plus W2 prime. Right? Well, this implies that W1 minus W2 is equal to W2 prime minus W1 prime. This thing is in W. This thing is in W prime. So whatever this common vector is, it's in the intersection of W and W prime, which is 0. But if this thing is 0 and this thing is 0, that implies that W1 equals W2 and W2 prime equals W1 prime. So the way we wrote these things as sums to start with was unique. Is that pretty clear? Are there any questions about this? Great. Second consequence. So now let's sort of forget about the sort of notation we introduced before. So we're just going to start with, maybe the same vector space V, but we're not going to have W defined as before. We're just going to let W be some subspace. So if W is a subspace of V, then there is another subspace there's another subspace W prime of V such that the composite map, so I can certainly just inject W prime into V by just letting W prime map to W prime. I mean, this is just sort of the embedding map. This is sort of the identity map on W prime. And recall also that there is a canonical map, and it's a surjection. There's a canonical quotient map, so canonical quotient map, which just takes this W prime and maps it to the coset of W prime, the W coset of W prime, such that this composite map is an isomorphism. So this is a great result. This is the result that was referred to at the very end of the last lecture, and for which there was a sort of counterexample given, or part of which there was a counterexample given to by a group theoretic, general group theoretic example involving the cyclic groups that we saw last week. But it turns out that vector spaces are nice enough that things sort of always break up in this great way. And I'll elucidate that further with a third consequence. But can anybody just give me very briefly the argument for this? Yeah, Emily.
Oh, I mean, if V basis for W, then there's the basis for V, and then the extra part of the basis will be the basis for W prime.
Exactly. So paraphrasing. The point is that we take a basis, call it V1 through Vn of W, extend to basis Vn plus 1 up through Vm of V. We're allowed to do this. Then we just let W prime be, as before, the span of, sorry, this should be V1 up through Vm, span of Vn plus 1 up through Vm. And then it's not so hard to verify that this has exactly the right property. The thing is, well, certainly a homomorphism. I mean, that it's a linear transformation follows just immediately by the definition. We chose these things to be linear transformations, and the composite of a linear transformation is a linear transformation. The surjectivity follows from the fact that we saw before that everything in V can be written as a sum of something in W prime and something in W. So if we take some element of V mod W, then I can lift it to something in V, write it as something of the form W plus W prime, where W is in W and W prime is in W prime, And then certainly the coset W prime plus big W must be the coset we started out with. Is that pretty clear? So surjectivity, straightforward from definition of cosets. And the spanning. So in general, in these sorts of results, whenever you see something that you need to be surjective, think about spanning. Whenever you need something to be injective, think about linear independence. These are just sort of general tips and tricks, and this is certainly going to be the basic argument in all the consequences of the result from last time that we started with. And so injectivity, well, again, this is a sort of linear independence type result. So if I have, I mean, I can certainly, we just saw it, I can certainly write any cosets in the form W prime plus W, where W prime is in big W prime. And so suppose I have two things which have the same image. Well, then we've seen that W1 prime minus W2 prime must be in W. So we have this thing which is in W, but it's also in W prime. And then again, by the same linear independence argument we saw before, this thing must be 0. So these must be the same cosets. Great. So let's look at a third consequence that brings together the first two consequences I've listed here. Yes, go ahead.
On the top line there, is that a capital W to the right?
So these are both
Those are the cosets?
capital W's. So the third thing is that if we put 1 and 2 together, put the arguments for 1 and 2 together, we get that for any subspace W of V, so suppose we have W subspace of V, there's an isomorphism between V and W with its product with the quotient. So V is isomorphic to W cross V mod W. And it's just a sort of exercise. I mean, don't hand this in or anything, but think about when you're reading over your notes why these two things come together to give this result. But it's just a very sort of cute result. It tells you exactly how to think about quotients and so on in the case of vector spaces. Don't be fooled. I mean, in general, in groups, quotient structures can be very, very complicated, very, very difficult. But in the case of vector spaces, it's very, very easy to understand quotients as being sort of complements. And a fourth result, well, actually, before I move on to a fourth result, can somebody tell me something as a result of this about the dimensions of V, W, and V mod W? Yes?
You got the dimension of V would have to be the sum of the dimension of W.
Yes, exactly. The dimension of V must be equal to the dimension of W plus the dimension of V mod W. Now let's use this result on a general linear map. So on a general linear map, so if f v to u is a linear transformation, then, well, two things are true. First of all, v is isomorphic to the product of the kernel of f with the image of f, and consequently, again, by the same argument as here, the dimension of v is equal to the dimension of the kernel of F plus the dimension of the image of F. What group theoretic result implies this? Yes?
Well, result that product of the order of the kernel with H, by the product by the order of its image is equal to
True. So that would be true if you had like finite groups, like say if this were over a finite field and we had a finite dimensional vector space. So what you were saying is you were referring to the counting formula that we looked at. But how did we prove that particular counting formula? There was a particular theorem that we saw. Yeah, there was the isomorphism theorem. So the key result that we previously saw, and it can't be emphasized how important this result is because it, in much the same way that our discussion here is completely informing the way we understand vector spaces, the isomorphism theorem we saw a few lectures ago completely informs the way we sort of decompose groups and understand their structure. So we saw a very significant isomorphism theorem. So why? Well, the isomorphism theorem for groups implies another sort of isomorphism theorem for vector spaces, where you just sort of add in the linear structure, which is something that's lacking in general groups. But here's a way of putting it. If I have a homomorphism, in fact, in our case, a linear transformation, because we want to preserve linear structure here, we're dealing with vector spaces. So given a linear transformation from some vector spaces V to U, the map F bar, remember we talked about the induced map? The induced map from V modulo the kernel of F going to the image of F, where we take V plus the kernel of F. A typical element of V modulo some group is V plus that subgroup. So we take this and we map it to F of V, which is a well-defined element of the image subgroup, or in our case, subspace. Is this familiar to everyone? Does everybody remember the isomorphism theorem? It's a very important result. In fact, if you don't remember it, I mean, I can't emphasize enough, it's a really great idea to go home and try to figure out how to prove it without looking at the book. It's very important. So the point is that this thing is a well-defined linear isomorphism. And we saw this in the case of groups. We saw that this thing is a well-defined homomorphism, and that it's injective and surjective by sort of basic properties of cosets. And so the only thing that's sort of being added here is the linear part. And that just involves multiplication by scalars. You just have to see that this map preserves multiplication by scalars. And this isn't hard. So given this result, all we have to do is take W to be the kernel of F, and then just put it in this result, because this is saying that V is isomorphic to kernel of F times image of F, and this is saying that, well, W times V mod W, but W is the kernel here. V mod W is V modulo the kernel, but that is, we've just seen, the image. So kernel times image. Any questions so far?
So we're really just taking a composition of the two isomorphisms.
Exactly. We're taking just a composition of the two isomorphisms. We're putting together all the things we know, we're accumulating them, we're putting together the isomorphisms, and we're seeing what we can find about the structure of the group. Now, in general, it's a very good idea if you're trying to understand the structure of a general group, and this is especially true of vector spaces, to try out various maps. Maps are giving you the structure. These sorts of theorems are telling you that you can take advantage of homomorphisms that you can find by various means to determine a lot about the structure of the vector spaces you started off with. They allow you to decompose maps and so on, decompose the vector spaces and so on. This is very, very true in the case of groups. You often can find some sort of homomorphism between groups and allow this to help you decompose the group into simpler structure. Okay, let's move on to something a little different. So, here's another sort of general problem for groups. Well, if I have a homomorphism between groups G and G prime, say, we want to find the kernel and the image of this homomorphism. Sort of a general problem. It's a sort of obvious thing that you want to be able to do. Now, this is, in general, very difficult. I mean, in fact, this is a sort of prerequisite for being able to take advantage of the kind of result that we're talking about here. But this can be very, very difficult in the case of general groups. This is generally difficult. But with vector spaces, it's easy. Yeah. Okay. And the main reason it's easy is because we have bases, and hence we can write things in matrix form, and we have all of these great algorithms like row reduction to help us find things like column spaces. So what I'm going to talk about for the rest of the lecture is how we make a translation between these sorts of abstract vector spaces and the language of matrices, and then use all those matrix algorithms that you learned in basic linear algebra to then lift back to these abstract vector spaces so that you can solve problems like this. So here's the point. But we can solve, in the case of vector spaces. The main tools are bases, matrices, and matrix algorithms. That you've all practiced ad nauseum. Yes, they are actually useful for something. So let's start looking at what I mean by that. In order to do that, I want to set up some correspondences. I want to set up some dictionaries here. So here are some correspondences. The first correspondence I want to set up is one that we saw in some form in last lecture, although it wasn't necessarily made completely explicit. So at least it was only made explicit in one direction. But let's review it because it's so important. So we saw last lecture that if V is an n-dimensional vector space over a field F, then bases correspond to something. Bases correspond to linear isomorphisms between the sort of canonical n-dimensional vector space Fn and V. There is a correspondence, a one-to-one onto correspondence between bases of V and linear isomorphisms from Fn to V. So suppose I have a basis And we're going to assume that our bases are ordered. So maybe I'll just put parenthetically that these are ordered bases. So suppose I have my basis B, which consists of vectors v1 through vn. We defined last time an isomorphism. How did we define it? Does anybody remember? Yes?
We have to be written as x1 times v1, etc. So we take this first x1 from x2.
Exactly. Paraphrasing and introducing a bit of notation, which isn't standard, it's not in the book or anything, but it's going to be a useful notation for the purposes of this lecture. We're going to define something I'm going to call rho B associated to this basis B. We're going to be going from Fn to V. And what will it do? Well, it'll take the column vector. I'll write, for the most part, elements of Fn as column vectors. You take the column vector A1 through AN, and you map it to the sum A1 V1 plus AN Vn. How do we go in the other direction? Suppose we have a linear isomorphism from Fn to V. What's the basis that corresponds to it? Yes, go ahead.
It would be the inverse of the matrix whose columns, it would be the inverse of F, I guess what you're calling rho B then.
Yeah, that's one way of putting it. So another way of putting it, so that one doesn't make direct reference to B as being a matrix. Why don't we think of this as just being some sort of ordered set? Another way of putting exactly what you just said is that if we have some rho, we take it to the ordered set rho of 1, 0, 0, 0, 0, and then rho 0, 1, 0, 0, and then onwards to 0, 0, 1. So there's this standard basis of Fn, and we just evaluate rho on that standard basis. So this is just a way of sort of translating everything into standard basis language. The whole point of this, the whole point of why this works, is precisely that Fn comes equipped with a sort of easy to work with basis. And a given abstract vector space doesn't necessarily. But by translating between the sort of canonical basis and whatever bases you might be able to find for your vector space, you're able to actually get work done. Okay, so in a word, why is all of this true? Well, this just follows from the fact that the interpretation we gave to a basis last time is that every vector in the given vector space can be written uniquely as a linear combination of those basis elements. This is simply a reinterpretation of that. So anyway, I refer you to your notes from last time to review exactly what's going on. But this follows from what we saw last time. Okay, the second correspondence I want to look at is something that you saw in basic linear algebra. And that is that linear transformations between our sort of standard vector spaces, Fn and Fm, these correspond to matrices. These correspond to M by N matrices over the field F. So another piece of notation just to make sure that we're all clear on what's going on here. I will denote the matrix associated to a linear transformation from Fn to Fm as square brackets F. What does square brackets F look like? Well, maybe in the language you saw before, this is the matrix associated to this with respect to the standard bases on these things. Well, that's just the matrix that looks like F of 1, 0, dot, dot, dot. And so this is an entire column here. So you have to think of this as being a matrix. So this isn't a 1. This is just saying that this is an entire column. And then I just evaluate on all of the standard basis elements all the way to the end. And I mean, this should be pretty familiar that this works. Going in the other direction, I take a matrix A, and from it I get a linear transformation from Fn to Fm by mapping a vector v in Fn to its matrix multiple by A. So this is just the standard thing we saw before. Now, one of the most important things about this correspondence is that it preserves the sorts of natural operations that you learned on both sides of that. So on the side of the linear transformations here, you know that you can add linear transformations and you can scalar multiply and you can compose. And the point is that that's preserved by this taking of brackets. So in brief, C1 F1 plus C2 F2 equals C1 brackets F1 plus C2 brackets F2. If I take the matrices associated to these things, it preserves all this sort of structure. And moreover, if I compose F1 and F2, well, that just corresponds to matrix multiplication. This is very important because we know exactly how to do matrix multiplication. We know how to do all these things in a very simple, efficient, algorithmic way. So this is a way of just translating into the language of matrices. So let's sort of put these things together, put these two correspondences together. So if I take correspondence this is 1 and 2, and I put them together, what do I get? Well, given some linear transformation from, say, v to v prime. So this is just some linear transformation. And let's assume that this thing has dimension n and m, and let's just equip these things with bases b and b prime. So these are these finite dimensional vector spaces of dimension n and m, and I equip them with these bases b and b prime. We know we can always equip a vector space with a basis. At least we showed that in the finite dimensional case. There is a proof that's more general that works in sort of the most general version of the theory of vector spaces, where you allow infinite dimensional vector spaces. But that requires a little set theory. So, and the controversial axiom of choice. So, given this thing, what do we do? Well, we have the matrix of F with respect to B and B prime. How do we define this? Well, let's just give it a notation, FB, B prime. This thing is rho B prime inverse F rho B. Why does this make sense? Well, we defined rho B so that it takes this standard vector space, these things of the form Fn, to the vector space we're working in. Then F takes the thing that, the vector space we're working in V to something in the vector space V prime. Then rho B prime translates back out of the abstract language of these vector spaces V prime and gives you something in this sort of canonical vector space Fm using this basis B prime. So it's the matrix of F with respect to B and B prime. Another sort of explicit way of looking at this is explicitly, if B is V1 through Vn and B prime is, say, V1, or maybe make this easier, W1 through Wm, then, well, given any of these Vj's, we know that we can write its image uniquely as a linear combination of things in this basis B prime. That was this defining characteristic of bases. So this thing looks like just the sum for each of these j's. J is just ranging over 1 through n. This looks like the sum I equals 1 to m aij wi for some scalars, aij. So what is this thing, f, b, b prime? Well, it's just this matrix made up of these numbers. And it's a very easy verification from this definition. This definition is just a sort of fancy and easy to work with way of introducing this more computational way of referring to the matrix with respect to b and b prime. And again, this sort of thing, so let's just actually just summarize this first of all. This thing sets up a very, very nice correspondence. This thing allows us to say that Hom v prime, by which I mean the set of linear transformations from v to v prime. This thing, in fact, has a vector space structure on it, and that's something we're going to sort of see in a minute. This thing is actually, given a choice of bases, essentially the same thing, or exactly isomorphic to, but in light of this particular choice, to the m by n matrices over F. This is just restating what we stated over here. But what I was just saying is that this thing has this nice sort of additional structure on it. I can add things in the set of linear transformations from v to v prime. I can scalar multiply them, and I can compose them. And the point is that the fact that the correspondence that we saw, the second correspondence we saw, the Roman numeral 2 correspondence, preserve that structure, implies that this Roman numeral 3 correspondence also preserves that structure. So, put explicitly, C1F1 plus C2F2 with respect to some b and b prime is equal to C1F1 with respect to b and b prime plus C2F2 b prime. Now, moreover, if I have, again, f v to v prime and g from v prime to v double prime, and again, I sort of equip these things with bases b, b prime, and b double prime, then exactly the sort of composition structure that you expect to be preserved is preserved. Again, this just sort of follows from what we saw before. So G compose F. So G compose F goes from V to V double prime. So I'd better take this with respect to bases B and B double prime. So B and B double prime. Well, this thing just looks like the matrix multiple of G with respect to B prime and B double prime with F with respect to B and B prime. It's just exactly the sort of composition that you expect. Is that pretty clear? Are there any questions? Yes?
The box that you've written around G, I should read that to myself as the linear as the matrix that does what G does.
Yeah, so what you should do is think of this alternatively as being the thing defined, the matrix defined by exactly this set of formulas, but replacing F with G and replacing these scalars with the ones that work for G, or just the thing that we defined before. This is rho B double prime inverse G rho B prime. This thing goes from the canonical vector space of the dimension of V prime to the canonical vector space of the dimension of V double prime, and we know how to write matrices for that. Is that clear? Cool. Okay. So we preserved the structure. We have all these great properties. What if we want to change bases? I mean, there's nothing canonical about a basis. There are lots and lots of bases for a given vector space. Sometimes you need to work in different bases according to the applications. Sometimes there are more convenient bases than the one that you started working with. So suppose in the middle of your calculations you need to start changing bases. how do you do this? Well, again, this is just a souped up version of exactly what you saw in basic linear algebra. This is just putting all the trappings of this theory of abstract vector spaces over an arbitrary field on a theory that you've already seen. So, change of basis. So suppose we have V, and it has bases B1 and B2. And we have vector space V prime over F, and it has bases B1 prime and B2 prime. Well, let's just sort of write out explicitly what F is in terms of the second vector space. So suppose you write this in terms of B2 prime. Well, we define this as being rho B2 prime inverse F rho B2, right? But I can always just sort of insert here, say, rho B1 prime, rho B1 prime inverse. That's just the identity map. So I'm certainly allowed to insert it here. And I can do the same sort of thing over here. So let me just write that out completely explicitly. I can rewrite this as rho B2 prime inverse rho B1 prime times rho B1 prime inverse F rho B1 rho B1 inverse. This thing again is the identity, so I'm just allowed to insert it wherever I want, as long as it's the identity on the right vector space, and it certainly is, rho B2. So I can, because of this sort of composition property of this taking matrices, this sort of bracketing operation. So this bracketing operation, you just have to think, okay, that means take the matrix. Well, we saw before that it preserves composition. So I could rewrite this as rho B2 prime inverse rho B1 prime times rho B1 prime inverse F rho B1 times rho B1 inverse rho B2. Why did I do this? Well, stuck in the middle here is F with respect to the bases B1 prime and B1. This thing is exactly equal to rho B1, B2 inverse rho B1 times F with respect to B1 prime and B1 times rho B1 inverse rho B2. And notice that the things on either side of this look very, very similar. Yeah, I mean, the primes should certainly be on the left. Thank you. Absolutely. So things that look like this, it makes sense to call change of basis matrices. So let's just give it that moniker. So call something of the form rho B1 inverse rho B2 the change of basis matrix. Or a change of basis matrix. In fact, it's unique given the B2 and the B1, but now, this is a bit general. You've probably seen this construction in a essentially identical form, but in the special case where V and V prime are the same. So if V equals V prime, then, well, I could just rewrite this as B2, B2. So again, I just have B1, B2. And so now these are bases for both V and V prime. This thing just looks like row B1 inverse, row B2 all inverse, because that looks like row B2 inverse, row B1. And I could remove the primes here because I'm just taking the same vector space, times F with respect to B1 and B1, times row B1 inverse row B2. So this is just the idea of similar matrices. This is something of the form P, F, B1, B1, P inverse rather, F, B1, B1, P, where P is exactly this changed basis matrix. Now stepping back to the general construction for just a second, let's just explicitly write down for sort of calculation purposes what that thing is. Well, if I have B1, and I can write it as V1 through Vn, and I have B2, and I write it as W1 through Wn, then row B1 inverse row B2 is just the matrix Cij, where I again use this sort of defining property of bases to write each element Wj as a linear combination of the Vi's, which I can certainly do. So this is I ranging over 1 to n. So to calculate, this is what you do. So if I just sort of think about this kind of thing that we've written down here, we've actually given this sort of thing a name. I mean, in basic linear algebra, you call this like the theory of similar matrices. But so far in group theory, we've given this a different name. That's conjugation of matrices. So what you have to start doing is in this sort of course, you want to start moving away from that language of like similar matrices and to the language of group theory. So you would talk about this as being conjugacy. And in fact, this totally makes sense because we actually have a group in which we're doing this conjugation. Let me make that explicit. So again, let's just start with some vector space V. So V is just some vector space. Well, then we define GLV to be the set of linear isomorphisms from V to V. So this is sort of the analog of the automorphism group of a group, except that we demand something additional. We demand not only that this thing be a group isomorphism, but that it preserve the scalar multiplication. So these are linear isomorphisms. But in particular, you can think of this as being some subgroup of the automorphism group of V just viewed as a group. So put another way, these are just the invertible linear transformations from V to V. Or, using a language that we've seen several times, what did we call the invertible elements of Z mod NZ? Exactly, Z mod NZ star. So it actually makes sense, given the notation we've introduced so far, to call this Hom V to V star. Now remember, the whole point of what we were just showing is that Hom V to V we can sort of translate into a new language, the language of matrices, given a choice of basis. So given a basis B of V, we just saw we can rewrite this isomorphically as the set of invertible matrices in in M n by n F, where n is the dimension of V. What is this thing called? What is the set of invertible matrices? GLNF. So the idea is that we have this abstract thing, GLV, but when we need to work with it, it's much more convenient to work with matrices because you can actually do calculation with matrices. And given a choice of basis, you can easily do this. You have an induced isomorphism with GLNF. And so it now becomes very easy to do whatever you want. Okay. The general point here is that you can set up this sort of dictionary. Just one last question to sort of feed your thought. In this language, in this sort of translation, what is the image of a linear transformation in terms of matrices? Yes? The column space, exactly. The image under this sort of dictionary is the same thing as the column space. We know how to find the column space of a matrix. So given an abstract vector space, we now have an algorithm for finding the image of a given linear transformation. The same thing applies to the kernel, because you can find the null space of a matrix, and that thing under this dictionary is precisely the kernel. So that's just food for thought.